Welcome to today's session. In this video, we will tackle an interesting problem titled Number of Equivalent Domino Pairs. Together, we'll explore the problem, break it down step by step, and discuss an efficient approach to solve it. Let's dive right in. In this problem, we are working with a list of dominoes, where each domino is represented as a pair of integers, a, b. The goal is to determine how many pairs of dominoes are equivalent. Two dominoes are considered equivalent in two cases: either they are identical in the given order, meaning the first number of one domino matches the first number of another, and the second number matches as well, or they are identical when reversed, such that the first number of one domino matches the second number of another, and vice versa. For example, the domino 1, 2 is equivalent to both 1, 2, and 2, 1. You need to find all the pairs of indices, I, j, such that I is less than j, and the dominoes at those indices are equivalent. The input is a list of dominoes, and the output is an integer representing the total number of equivalent pairs in this list. For the first example, the input list of dominoes is 1, 2, 2, 1, 3, 4, 5, 6. The output is 1 because the domino 1, 2 is equivalent to 2, 1 when reversed. There are no other equivalent pairs in the list, so the total is 1. In the second example, the input list is 1, 2, 2, 1, 1, 2, 2, 1, 3, 4. Here, the domino 1, 2 is equivalent to 2, 1, and it's also equivalent to the other 1, 2, and 2, 1 in the list. This results in multiple valid pairs of equivalent dominoes. To break down the second example further, there are 6 valid pairs of equivalent dominoes: 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, and 2, 3. This is why the total output is 6. The constraints for this problem specify that the length of the dominoes list can range from 1 to 10,000, and each integer in a domino is between 1 and 9. This means our solution needs to be efficient enough to handle up to 10,000 dominoes, even when the input size is at its maximum. Now, let's consider some edge cases. If the input list contains only one domino, such as 1, 2, there are no pairs to compare, so the output would be 0. If all dominoes in the list are identical, such as 1, 2, 1, 2, 1, 2, the number of valid pairs grows quadratically with the number of dominoes. For n dominoes, the total number of pairs is n times n-1 divided by 2. On the other hand, if no dominoes are equivalent, such as 1, 2, 3, 4, 5, 6, the output is 0. It's also important to account for reversed equivalence, where dominoes like 1, 2 are considered equivalent to 2, 1. Finally, when the input size reaches 10,000 dominoes, the solution must remain efficient and not exceed time or space limits. When tackling the problem of counting equivalent domino pairs, the primary goal is to identify pairs that meet the criteria of equivalence. Specifically, two dominoes, A, B, and C, D, are considered equivalent if their values match either directly, as in A equals C and B equals D, or in reverse order, where A equals D and B equals C. One initial approach to solving this problem is the brute force method. This method relies on directly comparing each domino with every other domino in the list. For each pair, you would check both possible equivalence conditions, either in the original order or the reversed order. While this approach is simple to understand and implement, it has significant drawbacks. The algorithm involves a nested loop, leading to a time complexity of n squared, where n is the number of dominoes. This quadratic growth in comparisons makes the brute force method impractical for large input sizes. Additionally, it doesn't utilize any additional data structures, so the space complexity remains constant at 1. However, a high computational cost makes this method unsuitable for scaling to larger datasets, such as when n is in the tens of thousands. To overcome the inefficiencies of the brute force method, we can adopt a more optimized approach that uses normalization and hashing. The key idea here is to standardize the representation of each domino. By ensuring that the smaller value always comes first, we can normalize dominoes such that A, B is transformed into min, A, B, max, A, B. This guarantees that equivalent dominoes will have the same representation regardless of their order. Once normalized, we can use a hash map to efficiently count the frequency of each unique domino. The algorithm involves three main steps. First, normalize all the dominoes. Second, populate the hash map with the frequency of each normalized domino. And third, calculate the number of equivalent pairs for each unique domino using the formula count times count minus 1 divided by 2, where count refers to the frequency. This approach achieves a time complexity of O(n), as the dominoes are processed in a single pass, and hashing operations are constant time on average. The space complexity is O(u), where U represents the number of unique dominoes, which is capped at 45 due to the constraints of domino values being between 1 and 9. This method is not only highly efficient but also scalable, making it ideal for large datasets. As an alternative, sorting the dominoes and counting duplicates is another possible solution. However, sorting incurs an O(n) log n time complexity, which makes it less efficient than the hash map approach. Additionally, sorting introduces overhead that can make the implementation slightly more complex. The strategy we ultimately chose to solve this problem is the optimized approach that uses normalization and hashing. This method stands out for its efficiency and simplicity, as it avoids the computational overhead of the brute force method and is faster than the sorting-based alternative. The core insight that makes this approach so effective is the idea of normalization, which allows us to treat equivalent dominoes as identical. By leveraging a hash map to count frequencies, we reduce the problem to a straightforward counting operation, achieving a time complexity of O(n). This makes the solution highly scalable, even for large input sizes. When evaluating the trade-offs, the brute force method is the simplest to implement but becomes prohibitively slow as the number of dominoes increases. The sorting approach, while more efficient than brute force, still incurs additional overhead due to the sorting step. In contrast, the hashing approach strikes the perfect balance between efficiency and clarity, making it the best choice. This combination of normalization and hashing not only improves performance but also simplifies the overall problem-solving process, ensuring an optimal solution for this challenge. In this problem, we're given a list of domino pairs, each represented as a pair of integers, a, b. Our objective is to determine the number of pairs of dominoes that are equivalent. Two dominoes are considered equivalent if either the pairs match exactly, meaning A equals C and B equals D, or if the pairs are reverses of each other, or A equals D and B equals C. The first step in solving this problem is to normalize each domino pair. Normalization ensures that we treat A, B, and B, A as the same, regardless of their order. To normalize, we always place the smaller number first in the pair. For instance, 2, 5 remains 2, 5, but 5, 2 is transformed into 2, 5. By doing this, we standardize the representation of each domino, making equivalence checks straightforward. For example, given the input 2, 5, 5, 2, 4, 4, 5, 5, the normalized output becomes 2, 5, 2, 5, 4, 4, 5, 5. This normalization step is essential as it prepares us for counting equivalent pairs efficiently in the next steps. After normalizing the domino pairs, the next step is to count the frequency of each unique normalized pair. This is important because dominoes that are equivalent will have the same normalized form, so by counting how often each normalized pair occurs, we can easily determine the number of equivalent pairs. To achieve this, we use a hash map, where the keys are the normalized pairs and the values represent their frequencies. We iterate through the list of normalized pairs, and for each pair, we increment its count in the hash map. For example, from our normalized input 2, 5, 2, 5, 4, 4, 5, 5, we construct a frequency map. 2, 5 appears twice, 4, 4 appears once, and 5, 5 also appears once. The resulting frequency map is 2, 5, 2, 4, 4, 1, 5, 5, 1. Once we have the frequency map, we can calculate the number of equivalent pairs. If a pair appears frequency times, the number of ways to choose two pairs from it is given by the combination formula, C, frequency, 2, which simplifies to frequency multiplied by frequency minus 1, divided by 2. For example, with the frequency map above, 2, 5, contributes one equivalent pair since C, 2, 2, equals 1, while 4, 4, and 5, 5, each with a frequency of 1, contribute no equivalent pairs. After iterating through the frequency map, we sum up all the contributions from each normalized pair to compute the total number of equivalent domino pairs. From our earlier example, the total is one equivalent pair. Finally, we return this result as the output. There are a few key insights to highlight in this algorithm. First, normalization is absolutely crucial. By always storing the smaller value first in each pair, we ensure that equivalent pairs like 2, 5, and 5, 2 are treated as identical, which simplifies the problem significantly. Second, using a hash map allows us to efficiently count the frequencies of normalized pairs in O and time, avoiding the inefficiency of a brute force approach, which would require O n squared time to compare all pairs directly. Lastly, the combination formula provides a quick and effective way to calculate the number of ways to select two pairs from a group, without needing to generate all possible combinations explicitly. Together, these optimizations ensure that the algorithm runs efficiently even for large inputs. The hash map plays a central role here, as it provides O(1) average time complexity for both insertion and lookup operations, making it ideal for our frequency counting step. Now, let's analyze the complexity of our algorithm. The time complexity can be broken down into three main steps. First, normalizing all the dominoes requires O n time, where n is the number of domino pairs. Second, counting the frequencies of the normalized pairs using a hash map also takes O n time. Finally, calculating the number of equivalent pairs involves iterating through the frequency map, which takes O k time, where k is the number of unique normalized pairs. Since k is always less than or equal to n, the total time complexity is O n. For space complexity, the hash map used to store frequencies requires O k space, where k is the number of unique normalized pairs. Again, since k is at most n, the space complexity is O n. Let's also consider some important edge cases. If the input is an empty list of dominoes, the output should simply be 0, as there are no pairs to compare. If all dominoes are unique, meaning no two pairs are equivalent, the output is also 0, as no equivalent pairs exist. On the other hand, if all dominoes are identical, the output is the combination of all n dominoes taken two at a time, which is C, n, 2. Lastly, in cases where some dominoes have equivalents and others do not, our algorithm correctly counts only the equivalent pairs while ignoring the rest. Let's walk through an example to solidify our understanding. Consider the input dominoes 2, 5, 5, 2, 4, 4, 5, 5. The first step is to normalize each domino. For 2, 5, the normalized form remains 2, 5. For 5, 2, the normalized form becomes 2, 5, as we place the smaller number first. For 4, 4, the values are already equal, so the normalized form is 4, 4. Finally, 4, 5, 5, the normalized form remains 5, 5. After normalization, we get the list 2, 5, 2, 5, 4, 4, 5, 5. Next, we count the frequencies of each normalized pair using a hash map. The pair 2, 5 appears twice, while 4, 4, and 5, 5 each appear once. This gives us the frequency map 2, 5, 2, 4, 4, 1, 5, 5, 1. Now, we calculate the number of equivalent pairs using the combination formula. For the pair 2, 5, which has a frequency of 2, we calculate C, 2, 2, as 2 multiplied by 2 minus 1, divided by 2, which equals 1. For the pairs 4, 4, and 5, 5, each with a frequency of 1, the combination formula gives C, 1, 2, which is 0. Adding these contributions together, the total number of equivalent pairs is 1. Finally, we return this result. The output is 1, indicating that there is exactly one equivalent domino pair in the input. This example illustrates how normalization, frequency counting, and the combination formula work together to efficiently solve the problem. This Python implementation solves the problem of finding the number of equivalent domino pairs efficiently. The key is to normalize each domino pair so that A, B, and B, A are treated as the same. We use a defaultic to keep track of the occurrences of each normalized domino pair. 1. Imports. We import defaultic from the collections module to simplify counting normalized pairs. 2. Initialization. A count dictionary is initialized to store the frequency of each normalized domino pair. The result variable will accumulate the total number of equivalent domino pairs. 3. Normalization. For each domino in the input, we sort the pair using sorted domino, ensuring A, B, and B, A, are treated identically. The sorted pair is converted into a tuple, since lists are not hashable, and stored as normalized. For update result, if the normalized domino already exists in the dictionary, its count indicates how many equivalent pairs have been encountered so far. We add that count to the result. 5. Increment count. Regardless of whether the domino was already seen, we increment its count in the dictionary. 6. Return result. After processing all dominoes, result contains the total number of equivalent pairs and is returned as the final answer. This approach is efficient with a time complexity of O(n), where n is the number of dominoes, as each domino is processed in constant time. The space complexity is O(k), where k is the number of distinct normalized domino pairs, at most 45, since there are only 9×10⁻² unique pairs. This is the Java implementation of the number of equivalent domino pairs problem. The logic mirrors the Python solution, where domino pairs are normalized by sorting their values to ensure A, B, and B, A are treated identically. A hash map is used to count occurrences of normalized dominoes, and the result is increment using the current count for each normalized pair. Key Java-specific differences include type declarations and the use of Java's hash map instead of Python's default dict. To solve this problem, we start by initializing an empty dictionary called count using default dict to store the frequencies of normalized domino pairs. We also set our result variable to 0, which will keep track of the total number of equivalent domino pairs. Now, for the first domino, 1, 2, we normalize it by sorting the values, resulting in the tuple 1, 2. Since this is the first time we've seen this pair, we add the current count of 1, 2, which is 0, to the result. The result remains 0. We then update the count 4, 1, 2 to 1. For the second domino, 2, 1, normalizing it also gives 1, 2. This time, the count 4, 1, 2 is 1, so we add that to the result, making the result 1. We then increment the count 4, 1, 2 to 2. Moving on to the third domino, 3, 4, normalizing it gives 3, 4. Since this pair is new, its count is 0, so adding it to the result keeps the result at 1. We then update the count 4, 3, 4 to 1. Now, for the final domino in this example, 5, 6, normalizing it gives the tuple 5, 6. This is also a new pair, so its count is 0. Adding this to the result keeps the result at 1. We then update the count 4, 5, 6 to 1. At this point, we've processed all the dominoes and the result is 1, indicating that there is exactly one pair of equivalent dominoes in this input. Moving on to the second example, we initialize our count dictionary and result variable again, both starting empty or at 0. For the first domino, 1, 2, normalizing it gives 1, 2. Its count is 0, so the result stays 0. We increment the count 4, 1, 2 to 1. Next, we process 2, 1, and normalizing it gives 1, 2 again. This time, the count 4, 1, 2 is 1, so we add 1 to the result, making the result equal to 1. We then increment the count 4, 1, 2 to 2. For the third domino, 1, 2, normalizing it still results in 1, 2. The current count for this pair is 2, so we add 2 to the result, updating it to 3. We then increase the count 4, 1, 2 to 3. Finally, processing 2, 1, normalizing it again gives 1, 2. The count now is 3, so we add 3 to the result, bringing the total result to 6. After incrementing the count 4, 1, 2 to 4, we conclude this example with a result of 6, indicating multiple equivalent domino pairs. In the third example, the input contains completely unique dominoes, 1, 2, 3, 4, and 5, 6. We begin by initializing the count dictionary and the result variable. For the first domino, 1, 2, normalizing it gives the tuple 1, 2. Since this pair is new, its count is 0, so the result remains 0. We then update the count 4, 1, 2 to 1. For the second domino, 3, 4, normalizing gives 3, 4. Like the first domino, this pair is also new, so its count is 0 and the result stays 0. We update the count 4, 3, 4 to 1. Finally, 4, 5, 6, normalizing it gives 5, 6. Again, this is a new pair, so its count is 0, keeping the result at 0. We update the count 4, 5, 6 to 1. After processing all the dominoes in this example, we find that the result is 0. This confirms that there are no equivalent domino pairs in the input. Each domino is unique, and our approach effectively captures this by maintaining and updating the counts of normalized pairs. This concludes the walkthrough of the solution, demonstrating how the algorithm handles different scenarios, including simple cases, multiple equivalent pairs, and completely unique domino sets. The time complexity of our solution is determined by several steps. First, we iterate over the list of dominoes, which involves a single pass through the list. If the list contains n dominoes, this iteration takes n time. Next, for each domino, we perform a normalization step by sorting its two elements into a tuple. Since sorting a pair of two elements has a constant time complexity, O1, normalizing all n dominoes results in O(n) asterisk O1, which simplifies to O(n). After normalization, we update the count dictionary. Operations on a hash table, such as inserting or accessing elements, generally take O1 on average. So, for n dominoes, updating the dictionary adds another O(n) to the time complexity. Finally, adding the counts to the result involves a simple arithmetic operation that takes O1 for each domino, contributing another O(n) across the entire list. When we combine these components, the overall time complexity of the solution is O(n), which is linear with respect to the number of dominoes. The space complexity of the solution is primarily driven by the count dictionary, which tracks the frequency of normalized domino pairs. Each key in the dictionary is a tuple representing a normalized pair, and each value is an integer representing the count. In the worst case, all domino pairs are unique, meaning the dictionary will have n keys for n dominoes. Therefore, the space required for the dictionary scales linearly, resulting in O(n) space. Additionally, we use a few auxiliary variables such as result, which is an integer, and normalized, which is a tuple of size 2. These variables occupy constant space, O1, and do not grow with the input size. As a result, the overall space complexity of the solution is dominated by the count dictionary and is O(n). The best, average, and worst-case scenarios all share the same time complexity, O(n), but they differ in how the count dictionary is used. In the best case, all dominoes are identical, so the dictionary contains only one key. Updating and accessing a single key is O1 per operation, and the total time remains O(n) because of the single pass through the list. In the average case, where dominoes are a mix of duplicates and unique pairs, the time complexity still remains O(n), as the dictionary operations remain efficient. The worst case occurs when all dominoes are unique, leading to n unique keys in the dictionary. Even in this case, each operation on the dictionary is O1 on average, so the total time complexity remains O(n). Comparing this to a brute force approach, which would involve comparing every pair of dominoes and result in O(n) squared complexity, our solution is significantly more efficient. By using a hash table to track occurrences of normalized dominoes, we avoid nested loops and achieve linear time. This efficiency is mathematically justified because the single loop processes n dominoes, dictionary operations are O1 on average, and normalizing each domino is a constant time operation. Together, these ensure that the overall time complexity is O(n), while the space complexity remains O(n). One of the most common mistakes in solving this problem is failing to normalize the domino pairs. Remember, a domino like A, B is equivalent to B, A, so it's crucial to represent all dominoes consistently as min, A, B, max, A, B. Without this step, the same pair could be counted as two distinct items, leading to incorrect results. Another frequent mistake is relying on a brute force approach, where every domino is compared with every other domino. While this method may work for small inputs, it results in an O(n) squared time complexity, which is inefficient and can cause time limit exceeded errors for larger datasets. Finally, improper usage of hash maps is another pitfall. If you use A, B directly as keys without normalizing, equivalent pairs like 1, 2, and 2, 1 could be treated as separate entries, making your solution fail to group them correctly. Hash maps require consistent keys to work effectively. Another common mistake is making off-by-one errors when calculating the number of equivalent pairs. For example, if a domino appears k times, the total number of pairs should be computed as k*, k1/2. Forgetting this formula or misapplying it can lead to undercounting or overcounting. It's also critical to handle edge cases carefully. Consider scenarios where all dominoes are unique or where every domino is identical. Overlooking these cases can result in runtime errors or incorrect outputs. Edge cases often expose hidden assumptions in your code, so it's important to test for them explicitly to ensure the solution is robust. When tackling this problem in an interview setting, normalization is a key concept to emphasize. By sorting each domino, you ensure that A, B, and B, A are always treated the same. Using hash maps is another important optimization strategy. They allow you to count the frequency of normalized domino pairs efficiently, achieving an O(n) solution. Scalability is a critical factor to consider. While brute force methods might work for small inputs, they are impractical for larger datasets, so always aim for more efficient approaches. Interviewers also appreciate when candidates think through edge cases aloud, such as scenarios with no pairs or all pairs being identical. Finally, recognize the broader pattern in this problem. It involves grouping and counting equivalent items, a concept that appears in related problems like anagrams, detecting duplicates, and working with subsets. This problem shares similarities with several others on LeetCode. For instance, problem 49, group anagrams, requires grouping strings by normalizing and using hash maps. Problem 532, k-diff pairs in an array, involves identifying pairs with a specific difference, also leveraging hash maps. Problem 1512, number of good pairs, focuses on counting index pairs where nums, I, equals nums, j, and problem 1288, remove covered intervals, emphasizes normalizing intervals to find relationships between pairs. As for alternative approaches, a brute force solution involves comparing every pair of dominoes. While simple to implement, it has a time complexity of O(n squared, making it inefficient for larger inputs. On the other hand, the optimal solution uses a hash map with normalization. By counting frequencies and applying the formula k*, k1/2, you achieve an O(n) solution. This method is efficient but requires a solid understanding of hash maps and frequency counting. Another approach to solving this problem is to use sorting combined with grouping. After normalizing all domino pairs, you can sort the list and then count equivalent groups. This method is less efficient than using a hash map because the sorting step introduces an O(n log n) complexity. However, it may be easier to implement if you're more comfortable working with sorted arrays than hash maps. While not optimal for large datasets, this approach can still be a practical alternative for solving the problem in certain scenarios. Thank you for joining today's session. We discussed an efficient solution to the problem number of equivalent domino pairs and highlighted key strategies like standardizing inputs and utilizing hash maps. These techniques are broadly applicable and can help you tackle similar problems in the future. Don't forget to like, share, and subscribe for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!